So good afternoon. Today we talk about text mining, which is data mining with text data. And this is the program I prepared for today. So we discuss first some text mining applications, some example of what can be done, how to represent text. And I guess you're familiar already with searching document in text. We will do also topic extractions and how to do machine learning with text. For a hands-on exercise, we will predict the number of views, or let's say we will predict if an article in the ISA News internet portal will receive a high or a low number of views. Applications, well, I think you know all these ones. Spam filtering is a clear application of text mining, where we have a prediction model that predicts if a document or an email is spam or not. Search is another good example, but a bit more fancy is, for instance, sentiment analysis. This is an application for trading, like stocks and so, where you get the for every news, and try to get the mouse. Let me just put the laser point in this area here. They automatically rank if it's a good news or it's a bad news. So you can see how the news affect the behavior of the market. This is just one application. Another typical application is to monitor Twitter, and then you can tell if people is talking good or bad about your brand. Other application, for instance, image captioning. You can give a picture to a neural network, and it will tell you, or it will describe what is inside the picture. All this caption has been automatically generated from the image. Translation, I think everybody uses Google Translate. And another application is the one we discussed, predicting ISA News number of views. So how does it work? We need to represent text as something else that can be ingested by machine learning. And there are several possibilities. One possibility is using Bagofwords representation. So let me tell you how it works. Imagine that we have two documents. So John likes to watch movies. Mary likes movies too. It's the first document. Second document, John also likes to watch football games, as a running example. No? So something we can do very simple is remove the punctuation, extract the words, and with this representation we can list all the words in an arbitrary order so that we don't have repetition. And having those, we can count how many times each word appears in each document. So we have, for instance, John likes, so likes is in the second position, and we have likes here, we have likes there, so that's where these two comes from. Here we have a 0, because in the first document there was no games. It's easy to follow. So the same representation again with a table, and a document will be a vector in an n-dimensional space, where n is the number of words, number of terms considered. So it's like having a point in an n-dimensional space, but for reasons that we will see in obvious later on, it's better to think of it as a vector. The issue with this representation is that it doesn't consider the word order. So different permutation in the word order will lead to the same vector. An intuition. Let's say that we have a document that only has 2 words, and we have document A and B. There we will see that they are similar documents, and if they have this shape, we will say that they are different documents. So let's work with this intuition a bit more. In this case, what will you say? Is a similar or different documents? It's a subset. So in this case, we will say it's a subset. So they are similar, but they have different length. And this is something typical when you're searching a document. The document typically is much longer than your search. So something like this. So how to quantify how similar they are? The trick is to consider the angle. And we use this operation, which is basically the cosine of the angle. And the closer it is to 1, the more similar it is. The closer it is to 0, the more different it is. So in this example, let's assume this is 70 degrees. So similarity is 0.34. Some other examples. The idea is that we are independent of the length of the document. So we are just based on the direction. Maybe in 2D it's not as obvious, but when you have many dimensions, the direction is a better discrimination than any other measure for this so high dimensionality. So when you're doing document search, basically what you want to do is find which are the documents which are closer to your query. So something you can do is compute the pairwise cosine similarity between the query and all your documents and return the top 10 that have a higher similarity. This will work, but we need to do some tweaks still, because this will yield some irrelevant documents. So let's work on how to make this more relevant. And to make it more relevant, something we can do is to reduce the number of dimensions. So we can remove punctuation. We can make, for instance, everything lowercase. So whatever the case, we consider is the same word. We can also remove what is called stop words, so words that don't add much information. And we can do stemming or lemmatization, which is putting the words in the root form, if you like, no? If you have child, you will get child, but if you have children, you get also child. So a simplification of the text. If we do so in our representation, this is what we get. So we reduce the number of dimensions. And this will work a bit better, but still we will return many irrelevant documents. So to gain relevancy, we will compute the term frequency as we're doing, but we need to take into account something else, which is the document frequency. If you realize there was 0 times this word appear in the second document, 0 times this document appear in the first document. So if in the, it's just like a toy example, no? But if somebody said my document contains, or my query is talking about football, you know that it's not the first one, it's already the second. Because this document, this word doesn't appear. So there are some terms, there are some words that have some more discriminative power than others, because it's only few documents that contain this word. Okay? To account for this fact, what we're going to do as well is to consider the document frequency. So we're going to check in how many documents each of these terms appear. So for instance, we have John appearing in 2 documents, like in 2 documents. So we see that if we have this information, it's not as useful as if we would query for football or game. Okay? So based on this intuition, we compute something that is called in information retrieval tf-idf, which is just dividing the term frequency, this would be the numerator, divided by the document frequency, denominator. And so it's tf divided by df, but by convention, people talk about the inverse of the document frequency. So this is the standard name to call that, tf-idf. So this will be the new representation of each document. So each document will be represented by a vector in an n-dimensional space, but will be change its representation based on this normalization, based on the term frequency and the document frequency. I didn't know if putting this or not, but at the end I decided that it's good that I speak about this. It's just to say that it's a bit more complex, a bit more tricky, so the real formula is this one. But I don't go into details, just to give you that this is the intuition is the same. It's just that it's a bit more tricky to compute, but not too much. So when you have the task of searching documents, something you can do is remove punctuation, do lowercase, remove stopwords, stemming your documents, tf-idf your document. You do the same thing for your query and compute the pairwise cosine similarity between your query and the document in this tf-idf representation. And then now you get relevant results, because you can see that also the frequency of the terms in the documents. Another thing we could do is with text mining is topic extraction. This is quite interesting. Let's say that you have a company and you look to Twitter or social media and so, and you want to know what people is talking about. So instead of reading everything, you will think that what people talk about is a combination of topics. And what you see in this screen is I did the same thing, but for the ESA News. So every article in the ESA News talk about a combination of topics. For instance, I don't know if you've seen that in the canteen, top tomatoes thanks to Mars missions. So it's talking about technology, company, businesses, a bit of Mars, ExoMars, rover, so the topic Mars is talking about image, Mars, is talking about ocean, water, climate, carbon, and about experiment in gravity. Looks accurate to me. This one, for instance, magnetic field is about swarm. And I mean, we can tell, we can work on this. You can see more examples after in the practical session. So how does it work? How are we able to understand which is that people is talking about, or what is the combination of topics? The trick is to do a matrix factorization. So basically, we have our tf-idf matrix, and we will say that this is approximately equal, so with some error, to the multiplication of two matrices, a coefficient matrix and the features matrix. So our tf-idf is what we see. We have as number of rows, the number of documents, number of columns is the terms, and we will say that the coefficients will be this part. So for every document, we know the intensity of each topic, and then for every feature, for every topic, we know which words correspond to this topic. Okay. What you see here as labels is the top 4, so you can run them to get the most importance. And this runs automatically, so the only thing you need to do is, I want to have 20 topics or 15 topics, and it runs everything for you. So you don't need to decide which words should go in each topic. It's everything automatic. The topics are created because these two matrices optimize or minimize an objective function, which is to reduce the error on the reconstruction. And there is, here we use the non-negative matrix factorization technique, which impose also the constraints that the coefficient and the features should be non-negative. So being everything positive is easier to understand what is that influence more. But it's a optimization process that minimizes the reconstruction error. It's a bit beyond of the introduction scope of the the lecture today, I would say. So if you want to do machine learning with text, in all the previous lecture, we have discussed about regression, supervector machines, decision trees, neural networks, anomaly detection. So if you want to use machine learning with text data, what you need to do is transform text to numeric data, and then do machine learning as you will also usually do. So we will see an example on the ESA news later on. I wanted to show also another representation of words in addition to the tf-idf that we discussed. It's the one-hot encoding. So you can represent each word or every term like an array, very sparse, where you have a 1 in an arbitrary position. For instance, John will be the first position is set to 1, everything is 0. Like is a second position. And the issue here is that you might have very long number of words, so you maybe have 1 million different words, so this can get very sparse. This you can use, for instance, for language translation with recurrent neural networks, where you can put one word in this representation, the second word, the third word, and you get words back in the translation. The issue is that this can be very, very sparse, and this causes the machine learning to be very complex, because you need, if you have like 1 million words, you need 1 million inputs in your neural network, and it's hard to train. So what about if we can have another representation which is denser instead of sparse, and with a smaller number of dimensions, let's say 300. The way to do this is to use a neural network in a, let's say, non-orthodox way. So if you have this sentence, we will have the one encoding here, and also a one-hot encoding there. And this is how we train it. So we select a word here, for instance, John, and we want to predict any of the words which are in this context. For instance, likes is in the context, so 1 and everything 0. We go again and say 2 is also in the context, so likes now is 0, and 1 is to the 2, and we continue, so on, and we move the window. So basically the idea is you select the word here in the middle, and it needs to predict any which is in the context. This is a bit weird, because you will never get a perfect forecast, because sometimes for likes, for 2, for instance, which is in the middle, sometimes the right solution is likes, some other is watch, and if you use document and document and document, you have every time different words. But the point here is not to predict, is use the mechanism of prediction to find a representation, like minimizing the error, you get an encoding. So you keep doing this, and you have a representation, it's called embedding, that if you use, for instance, 300 dimensional embedding, you will use 300 neurons. And by minimizing this error on building this network, you will have an optimal representation that has some interesting properties. I show you the properties you can achieve with us. So words that are close in the embedding space are similar. So what I mean? I ask which is the most similar to Germany. And I got German, Europe, European, Sweden, Switzerland. So this, by the way, this has been extracted. This is a pre-trained embedding that is made available by Google, and is trained on billions of news articles. So it's according to the news article that Google trained it on. Maybe you've seen this in the news. You can do algebra in this vector space. So I can do king minus man plus woman, and I get queen. So you can use this to use to find analogies, like king is to man as woman is to queen. No, I did it wrong. No, it's man is to king. as woman is to queen. I need to fix this one. So this is what you did, basically, is positive. So the thing you want to add, negative, and well, this is what you get. You see the distance is by the way the cosine distance. So I try here smaller minus small plus big, so I get bigger. So you see this is a more subtle than using the dimensions, because somehow understands that words that are closer in this vector representation have similar meaning. And this is because the way they appear together in the text. Good news is that you can do this yourself, but there are the most famous pre-trained embeddings are this word2vec from Google that I mentioned before. There is another one from Stanford that is using a bit of different technology, but what you need, which is the vector with a smaller representation, is already available. So the advantage of word embeddings is that you can use simpler models, and it allows to recognize similar words. So it understands that some words are more similar than others. In the other representation, where you have dimensions, even if they're synonyms, it will be like another different dimension. So it doesn't take this into account. And for me, the best is the transfer learning. Imagine that you have very few documents yourself, like 1,000 documents, and somebody is doing a query and is not using exactly the same terms or the same words that are in your document. With this approach, since you're reusing a lot of words, it can figure out that some words are similar to the words that you have yourself. So it doesn't need to be exactly the same word to be found. And now that you know all this, I hope you can get this embedding joke. I'll leave it for you. So you can have some embedding humor there. So this is a bit what we discussed today. Some text mining application, text representation, how to do search, topic extraction, machine learning, and word embeddings. I have a project pitch, so on text mining, as a proposal. Let's see if you like everything. Everybody knows ART, so the anomaly report tracking system, and I have this idea. Imagine that mission A have report an anomaly, for instance, ground segment, and the mission B might have faced and possibly solved the same anomaly. And mission A doesn't know about the mission B resolution, and we can use text mining to automatically find this situation and contribute to the resolution of anomaly in mission A. So if somebody is here from mission A or from mission B and want to support this project, talk to me after. As usual, the presentation will be available in the ESA Connect community, and all the videos are also in the intranet. And the hands-on session will be on text mining on ESA News. Before going to the hands-on session, maybe we stop here to check if you have any question that you might want to ask.